In this lecture, we're going to discuss the other sensor that's on your Hapkit, which is a force-sensitive resistor. Force-sensitive resistors are essentially made out of a conductive polymer, which changes its resistance when force is applied. So like the magnetoresistive sensor that you have to measure position, it uses a change in resistance in order to make a measurement. What happens in an FSR is that more current can flow between conducting electrodes. So these gray lines here, which are interdigitated or interwoven, can send current between them when force is applied, because then the material which is in between has a resistance which decreases when a force is increased. So this is a picture of the different components of an FSR, including the flexible substrate that has the printed conductive polymer on it, a spacer adhesive, as well as a flexible substrate which has the electrodes printed on it. This is a picture of the actual FSR that comes with your Hapkit, which is connected to some leads, which will then go and plug into the Hapkit board. The specific FSR that you're given with your Hapkit has some specifications as follows. First of all, it has an active area, which is a circular area at the top, which is about 1/2 inch in diameter. It's only active in this area, so if you press on the long, thin part of the sensor, it's not going to register any forces. It has a variable resistance, as mentioned, and when there's no applied pressure, the resistance is very high, something on the order of a mega ohm. However, if you apply a light pressure from the finger, the resistance is still high, but not nearly as high, on the order of 100 kiloohms. And as you apply more and more pressure from your finger, the resistance can become quite low, on the order of 100 ohms. So in this way, you can measure the pressure from a finger or some other object on the sensor based on the change in resistance. Now, FSRs are not very accurate compared to load cells or force sensors based on strain gauges and other technology. In fact, the accuracy ranges pretty widely. It depends on how it's mounted and how you touch it and the consistency with which you apply pressure. And these are the manufacturer's specifications from 5% to 25% accuracy, but I have to say that in practice it can often be even worse than this. If you want to know the details about your FSR, you can download the datasheet from this URL. We purchased these force sensors from a company called Pololu, but they're made by a company called Interlink Electronics, which sells a lot of FSRs. So the datasheet written here actually comes from this company, Interlink Electronics. So some properties of force-sensitive resistors are important to review. In particular, the advantages and the disadvantages. The advantages, which are all the reasons why we chose this sensor to include in your Hapkit, is that it's very small and thin, so it's very easy to mount onto a device. In this case, there's an adhesive backing on the FSR, so you just stick it on and you're ready to go. They're very inexpensive, on the order of a few dollars. We have force sensors that we use in our laboratory, which are much more complex and can cost on the order of thousands of dollars. But you do get what you pay for. So the last advantage is that it's extremely easy to interface with electronics. Because all you have is a resistance that changes with applied force, you can use a simple circuit. What we actually use is a voltage divider, which, if you know circuits, is a basic type of circuit that you'd be familiar with, that you can use in order to figure out, measure a voltage across the force-sensitive resistor and see how that voltage changes. Your Hapkit board actually has some other components, particularly a resistor on it, which allows you to create this voltage divider, and you don't need to add any hardware or circuitry in order to use the FSR. And in fact, we don't even really care so much exactly what those component values are, like what the value of that extra resistor is, because we're going to do a calibration for the FSR anyways. Some of the disadvantages of FSRs, as I mentioned already, include that they are inaccurate and imprecise. They really only provide qualitative results. They're nice for user interfaces because they can tell you something about pressure being applied or contact being made, but it is true that they're not designed to take really precise data from an environment. For that, you would want a more expensive device. But despite this disadvantage, we have been able to successfully create some measurements of real environments based on the Hapkit position sensing and force-sensitive resistor sensing. And so for the purposes of displaying information on your Hapkit and recording data from the environment, it still can be useful. Another disadvantage is that the FSR has this region over which force is applied. There's that whole half-inch diameter circular face. And the FSR requires consistent force distribution over this surface in order to have consistent readings. This can be a problem if you make contact in some small area of that sensing, active sensing area. Then you might get different results if you've contacted it in a different area. So we've tried to pick a size that about matches the size of the human fingertip and covers the whole tip of the handle of your Hapkit. Here's a picture of the FSR on the Hapkit. When you've assembled it, you should have put your FSR active portion right here near the top. The leads will be traveling down the handle. We should try to make them as flat as possible, but just due to variations in manufacturing, sometimes it bows out a little bit like this, and that's okay, but you want to try and make it as flat as possible. And then there's a specific little notch where you would have glued in your connector or leads. And then the leads will travel down, go through a special hole in the plastic height adjustment bar. Note that if you're left-handed, you would have put the hole on the other side, and the FSR would have been flipped onto the other side here. But in this case, this is sort of for a right-handed user, so they would want to be pushing with their right hand, looking face on at the Hapkit, and so we put the FSR on the right side of the handle. In any case, these connector leads go to the Hapkit board. What's happening over here is showing the back side of your Hapkit assembly. Now the leads are traveling down and attaching to the board on a special connector right here. While you could make your own circuit by connecting the FSR leads to one of the analog input pins, for example, the analog input pin and an analog input ground, this is the connection point that you should use because it includes the resistor that creates the voltage divider that allows us to measure a change in voltage across the FSR in order to come up with a measure of force applied. So to use your FSR with your Hapkit board, of course you need to write some code. So I'll walk quickly through the basic commands that you need to use in order to do that. The first is that you need to define which pin the FSR is connected to. And because we've assigned a special connector to the FSR, at least in our current setup, this pin is fixed. And so this is the analog input 3 pin. So you'll want to have something in your code that says something like this. There's an integer FSR pin, which equals A3. Then you'll want to have something else in your code that actually reads the voltage on that FSR pin. And we've seen this function before, the analog read function. So remember that this is going to put out a value between 0 and 1023 because that's the digital resolution of the A to D converter on your Hapkit board. So the analog read will be assigned to that particular pin. Finally, you need to have some sort of FSR calibration code. When you actually start using the FSR in the 5th week, we'll go through those calibration steps. Basically, what you'll be doing is assigning a force value, hopefully in newtons, which is going to be a function of whatever FSR value is read based on the analog read function. But this function here is a function that you're going to generate. Just like you had to fit data, you have to fit data for the MR sensor in order to come up with a calibration for that one. You will also have to calibrate your force-sensitive resistor. And we'll determine this function in the 5th week of the class.